Good afternoon and welcome at the webinar of the MISafe package. I'm Minder de Vries, the coordinator of the FAST project, and I'm going to talk you to introduce you to the package and give you a quick overview of the rest of the program of this next 2 hours. The other experts of FAST are online and waiting for the chance to share information with you. Again, welcome to this webinar, and let's go. The structure is the following. I will give you a short introduction. Then we will discuss the science behind the MISafe package for 45 minutes. Then we will take a first round of questions, and we will then discuss the value of MISafe. And then we will conclude this 2 hours with a second round of questions of 20 minutes. And of course, on your own panel, on the right-hand side of your screen, you will see a questions panel. And in this questions panel, you can type your questions, and we will online try to answer these questions, but also we will record all your questions. In fact, we will record this whole webinar. And in a week from now, the webinar will be produced online, including these PowerPoints, and you will be notified by this because we know about your email addresses. So, short introduction to this MISafe package. To start, of course, we are developing a resource to implement nature-based flood defenses. And the rationale behind that is that these nature-based flood defenses are becoming recognized as a very sustainable and cost-effective strategy in this 21st century of increasing sea levels and climate change. We have been noticing that a verifiable demonstration of benefits has been lacking until now of nature-based flood defenses, that professionals need trusted and practical tools that can deliver for them quantitative information on key flood hazard parameters. And the FAST project, by setting up this MISafe product package, is trying to deliver at least some of those parameters. For the FAST project, we have defined a number of objectives that we adhere to in the period of this project, which is running from 2014 to 2017. We want to develop a Copernicus downstream service by developing open source products based on Sentinel data. And we want to gain from these Earth observation data from the Sentinels spatial information on foreshore and floodplain characteristics, such as information on the morphology, on the sediment characteristics, and on the vegetation properties. And for this, we built a product called MISafe that is supported by a number of services and SLAs. The MISafe package uses open source and open data concepts as basis, meaning that we try to share what we have developed, and we make available the data that we have been gathering. In the FAST consortium, you find 5 institutions in 4 countries. Deltares is the lead institution. I, the coordinator, am from Deltares. Other institutions are, of course, the University of Cambridge. Iris Muller is online, listening in and going to present in a minute. GeoEcomar, our colleagues from Romania, the NIOZ, the Royal Netherlands Institute for Sea Research. Daphne van der Wal is listening in and will continue presenting in a minute. And the University of Cadiz. Dr. Gloria Peralta is also listening in and will present her part in a minute. The FAST project itself is organized in the following structure. The management coordination done by us, by the Deltares. The content is generated in the work packages 3, 4, and 5, where we do the remote sensing, where we do the biophysical ground referencing at case study sites, and where we do the data integration and the tool development. And in work package 6 and work package 7, we have been working to disseminate the results, and we are now in the phase of demonstrating the product package that we have prepared, called MISafe. In this point, I will conclude my short introduction on the project and will give the podium to the work package leaders of the three work packages where the content has been generated. And the first of the work package leaders is Daphne van der Wal of the NIOS, and I will give the podium to her. Daphne, here you go.
Thank you, Mindert. So yes, we will now focus in this webinar on the remote sensing as part of MISafe. And we use remote sensing to assess the characteristics of the foreshores, to understand how foreshores function, and also as a base to predict their value for flood defense. And the remote sensing in FAST and in MISafe relies heavily on the European Copernicus program, because MISafe is a downstream service, Copernicus downstream service. Within this Copernicus program, there's a series of satellites to observe the land, the atmosphere, and the oceans. And I will show you how we retrieved information on foreshores from especially the Sentinel-2 satellites in particular. And well, these satellites have a multispectral imager on board, MSI, and at the moment, well, there's two Sentinel-2 satellites that are in orbit, and together they revisit a place on Earth every 5 days under the same viewing conditions. The data that are required are of the land surface, so including inland lakes, but also the coastal zone. So that means in this case up to 20 kilometers from the shoreline. And they gather that information in 13 spectral bands, as you can see here. So not only blue, green, and red, as you would normally have in a picture, but many more bands, many more wavelengths, and this enables us to better characterize the land surfaces and the coastal surfaces, in particular to characterize the vegetation characteristics. And the spatial resolution, you can see that in this column, varies from 10 meter to 60 meter. We make particularly use of the spectral bands that have a 10 to 20 meter spatial resolution. Well, apart from these Copernicus satellite centers, we also make use of the Landsat missions. You can see here the spectral bands that it acquires information in. It has slightly less bands, also a slightly lower spatial resolution, but it has a big advantage, and that is continuity. As you can see here, there's a long period of Landsat missions that have built up a large archive of data. So if we're looking at long-term changes, then these Landsat data are very valuable. Well, for FAST and for the MISafe viewer, we make the distinction in geospatial data products between global products available for the whole world and local data products, which can also be available for the whole world, but we focus here on the 8 pilot sites. And Mindert already showed you this map of our 8 pilot sites in the UK, in the Netherlands, Westerschelde Estuary, Romania, the Danube Delta, and in Cadiz Bay in Spain. And this is an overview of the geospatial data that we collected and developed. You see they're distinguished here between water level and waves, elevation, and vegetation. There's data that were already available. There's also data that we developed within FAST based on these Landsat and Sentinel 2 satellites. So I will go through them one by one and show you results of that. So first, water levels and waves. I will not go into detail here. This will come back in the presentation by Kees. So we'll be short on this, but that includes, for example, available existing data on extreme sea level predictions. For elevation, there is SRTM data, so shuttle radar topography mission data for the entire world, complemented by ASTER data, very coarse, but available worldwide, and then combined with oceanographic data, bathymetric charts. Well, as I said, quite coarse, but it's also very detailed information, for example, from laser altimetry, combined with, for example, single beam data or multi-beam data for the subtidal parts. This is an example from the Netherlands where such data is available, but you could imagine that that is not available for many places on Earth. And that's where FAST comes in, because within the MI Safe package there's a product called Global Intertidal Elevation that is developed. It's based on global data of a large time span of Landsat data and also the Copernicus Sentinel-2 data, and it's developed in Google Earth Engine. So using a whole stack of data in a procedure that is outlined here. I'm not going into detail here, but this is basically the broad scheme that is used after pre-processing, correcting for clouds, for example. For each of these images, a water index is calculated, and that is based on information on the shortwave, infrared, and green. That is then used as a whole stack of images to calculate an average per pixel. From that, an inundation probability can be derived, and with the help of tide data available globally, an elevation is then produced. And that results in elevation maps, for example, here for Cadiz and here for Tillingham in the UK. That was also validated by ground data as collected in FAST, DGPS data at the pilot sites for Spain, the Netherlands, and the UK, and also on a quite larger scale, drone data, structure from motion data, and laser altimetry. And you can see how that relates to the elevation as derived from the satellite. Well, in addition, it is tested for 2 sites in the US, and again tested against laser altimetry data in this case. Well, then we move on to vegetation. Again, there is information there on a global scale, on a European scale. This is an example of the Korean land cover that has been reclassified here to suit the needs for the MI Safe package here, to focus on the intertidal areas and the marshes. But again, it's quite coarse. So for a more detailed view, also available locally on sort of vegetation, absence, and presence, this product was developed again in the Google Earth Engine based on Sentinel-2 data, in this case of the coastline of the world. And here a stack is used of NDVI, so vegetation index, which relates to biomass of vegetation, also a little bit of health and type of vegetation. Well, that whole stack of all these data is averaged, and then with some processing, for example, taking into account seasonal variation, a vegetation presence absence map is made, as you can see here, for example, for the Westerschelde. But of course, vegetation is not static. It can change in time. And this is where the global vegetation change map comes in. It looks at vegetation gain and loss, looking at the Landsat archive and comparing the presence of vegetation in the 80s against presence today. Well, then the NDVI, the vegetation index, is also presented here as snapshots in time for all of the case study areas on a very detailed scale, again based on Sentinel-2 images. See here an example from Cadiz Bay and from the Romanian side in the Danube Delta. They only are taken sort of 1 day apart, but you can see already big differences in the NDVI, much greener in the reeds of the Danube Delta than in the Spartina stands in Cadiz Bay. You can also see the blue, and these are negative NDVI vegetation values, whereas the greens here represent the marshes. Well, again, we have that in time here. So here is seasonal development, which is also validated by in situ measurements. And then finally, we used and retrieved information on the leaf area index of the marsh, so the one-sided green leaf area per unit ground surface area. Again, from Sentinel-2 images, and what you can see an example here again for the Romanian side for 2 snapshots in time. And what you can see what it looks like here in the field. And with this image from a field site, I will hand you over to the next speaker, which is Iris Muller.
Hey, thank you, Daphne. Very clear. Iris, I'm going to give you the podium now, the floor.
Okay, thank you.
There you go.
Okay, thank you. Thank you, Mindert, and thank you, Daphne. So it's clear from the presentation we've just had that there is then a step required whereby we link the remotely sensed information to more detailed information on the ground. And that is really required because ultimately we sit within the context of our main aims and objectives, which are to calibrate the Earth observation algorithms at our field sites, but also obviously to see whether they are more generally applicable around the world, and of course to calibrate ultimately our estimates of wave reduction over these intertidal foreshores, so that they can be fed into general rules and predictive models which are then available through the MISAFE package. So we are now here at the bottom here. You've already seen this image in the presentation just now, where we're looking at our field measurements and the different sorts of things that we measured throughout this project. Now we had 3 key questions here really. The first one is what coastal wetland attributes actually affect water levels and waves, and we wanted to capture all of those. Secondly, what aspects of the coastal wetland give us a clue about its stability. Clearly we're interested in that wetland remaining in place for a considerable period of time so that we can rely on it as a coastal defence. And do those aspects relate to what we can see from the air or from space, and in what way do they relate to those measurements? And we've heard about those measurements already. So to answer these questions, we need to measure a whole range of things, and at the bottom of this slide here you can see a little diagram here that basically explains the difficulty of doing that. Clearly when the tide is out, those wetlands are generally exposed, or when there is low flow in river mouths or estuaries. When there is high flow or the tide is in, which happens rather frequently in some locations, then it's very difficult to get to these environments. So measuring directly is always a challenge, which is why remote sensing is such an attractive possibility. I've also tried to indicate here that one of the main things we need to characterize is the type of surface here, and that clearly consists of vegetation, and it consists of certain roughness elements like the type of sediment, the presence of topographic features like channels or depressions and so on, and how they interact with the water currents that are generated by tidal flow and waves, so that we can then look at the pressure on the high ground, the dike or the seawall that lies landwards of all this. So we know that those attributes that we're interested in vary by location, and they vary over time. You've already been introduced to these 8 case study sites. I'm just going to put a few photographs here so that you get a mental picture of what they look like. So we have 2 sites in the UK, Donnanook on the Lincolnshire coast and Tyneham on the Outer Thames Estuary on the Dengie Peninsula. Then we have a couple of sites in the Netherlands on the Schelde Estuary, one that's northward facing and one southward facing. We have a couple of marshes in the Bay of Cadiz, and we have these very seasonally changing reed beds in Romania, and I think you can see from those pictures there how much they change across the seasons. We measured 5 key aspects of the wetland surface, and the first one here is the incoming and reflected radiation. This clearly varies depending on the type of surface you're dealing with, and we're interested in linking these to what the satellite sees so that we can start to validate and calibrate our hydrodynamic models with the characteristics of that vegetation that matter in terms of flood and wave protection. So the vegetation is the second thing that we need to measure, and it's really the biomass, the structure of that vegetation, and there are various ways in which that can be measured, and we've used some quite innovative techniques such as side-on photography to complement more traditional techniques of measuring vegetation characteristics. The third one is the measure of the type of sediment and topography, and here we've really had extensive sampling of surface sediments to look at their size, the composition, organic matter present, the roughness features that are present on the surface, things like wave ripples, mud mounds, channels, depressions. All of those things are really important in their interaction with water flow and waves when it matters to us. We've also looked at shorter term fluctuations of those features in terms of how they change between tides, how they change over a year in terms of how much sediment comes in, how much sediment is deposited, and whether the wetland itself changes its characteristics, its internal structure, if you like, over time. And then lastly, of course, the 2 key measures here are measurements of water depth and measurements of waves, which we must have if we want to make sure that our tool gives us accurate predictions in terms of the protection that these wetlands provide to flood risk related processes. So I'm going to take you through these measurements in a little bit more detail here, just to make this a little bit clearer. When you go out to these kinds of environments, I've already mentioned that it's extremely challenging to get there. Clearly you can't often get there by boat, it's simply too shallow, and the inundation depth, the depth to which the water covers these surfaces is highly unpredictable, often mediated by meteorological effects, wind directions, atmospheric pressure and so on. And access on foot is also extremely challenging, largely because then you are dealing with water that is too deep. Or mud that is too deep. And so we've had to be a little bit flexible in terms of how we measured, and what you can see on these 2 sites here is a series of sort of blue dots which are our wave measurement stations which are aligned in a direction that's vaguely shore normal, a compromise between shore normality and the predominant wind direction at most of the sites. And then we have measurements that are these dots around them that refer to either measurements of sediment characteristics or vegetation characteristics. And the site on the right there is the reed bed site in Romania, which is virtually impenetrable. So the reeds were samples from the edge and then from the landward and the seaward edge largely. So the first thing we did is to approach these measurements with a view to validating our remotely sensed imagery, and for that we need spectrometers, which are devices that you can carry out into the field, and they record the reflected radiation from the ground and the incoming radiation to the ground. And we had 3 instruments which we had at the different institutes, and they had to be cross-calibrated, and this is really, really important to make sure that the scientific information we get out of this is high quality. So we deployed our instruments over a series of known surfaces. And there's an example here of clover, grass and concrete shown with wavelengths on the horizontal axis, and then the reflectance values on the vertical axis. And our 3 instruments performed relatively similarly, but there are subtle differences, and these differences have to be known clearly in order to then deploy these instruments in the field. Which we were then able to do. So we were then able to collect detailed field spectra at locations that are commensurate in scale with our sampling of the vegetation characteristics, which was largely done on a 1 by 1 meter quadrat basis, as you can see in the bottom right here. So in the top left you have an example of one of those reflectance spectra from the field with wavelength again on the horizontal axis and reflectance on the vertical axis, and you can see that that spectrum, the blue line is our continuous field spectrum, corresponds to some extent to what we might expect theoretically a vegetation spectrum to look like, which you can see in the top right there, the stippled line in that B plot. But it does deviate from that slightly, and those deviations are really important because they relate to the properties of that vegetation that potentially affect the degree to which that vegetation reduces the energy of waves and water flow across it. You can also see in the bottom left that when we take measurements that correspond to different wavelengths as sampled by Landsat or by Sentinel-2, and we convert them into NDVI by doing the appropriate computations over time, and here the x-axis is time, you can see that those measurements vary quite a lot, but that they're relatively well calibrated between our field spectra and the spaceborne platform measurements from Landsat and Sentinel-2. So we can use these relationships to look at seasonal changes in these vegetation properties. And we pick these seasonal changes up also when we sample biomass from these plots, and this was done directly by harvesting the above ground plant matter and then drying it and weighing it. And you can see in that plot at the top there that the biomass really does vary quite a lot seasonally at the different quadrats. Shown on the x-axis are lots of different quadrats that were sampled at our UK site, and here that red quadrat is just illustrated by the top-down photographs here, and you can see the seasonal change visibly in those photographs. What is interesting then is to relate that kind of change to the structure of the vegetation, and we've deployed some quite innovative measurements for bed roughness, both of the vegetation, which you can see on the left here, where the vegetation is photographed from the side, and then you can get all sorts of measures of the height, the structure, the density of the vegetation from that, which you can then feed into the hydrodynamic models. And you have on the right-hand side a roughness board, which tells us that the roughness across our field sites on the unvegetated tidal flat was already really quite different you can see on the bottom plot here that between Spain, the Netherlands and the UK, we saw quite a varied amount of bed roughness on the fronting tidal flat. And we can scale this up, of course, if we have high precision unmanned aerial vehicles or drones, which we have also used within the FAST project. And these can be used then to get a much more extensive spatial map of these vegetation properties, the NDVI, but at a resolution that is much higher resolution than we can get from spaceborne platforms, and that is much easier to relate to our field measurements. So we have effectively an intermediate scale level here that we can use for the cross-validation calibration between the field and the spaceborne platforms. And on the right here you can see that we can also get very detailed elevational maps from that can pick up the roughness elements that are present on those surfaces. As part of those kind of measurements, we're clearly interested in also in the temporal change. So rather like with the vegetation, we also want to know how the surfaces here respond to wave impact and tidal currents and perhaps seasonally changing sediment loads. So we have used a whole range of different measurement techniques here. SD sensors on the left, which use light diodes to look at variations in the bed level. We've looked at the sensitivity of the surface to shear forcing with a tall vein at the top, and then we've got sedimentation erosion tables that record the bed elevation over longer timescales, and I'll say a little bit more about that in a minute. What is important, of course, is that all these measurements are sort of situated on an elevational gradient generally when you're on the coast, and that elevational gradient is very important when you look at what happens to waves propagating towards the shore. And as you can see from these two plots here, which show a cross-shore coastal profile where the distance from the land to the sea is from the left to the right in these plots, given in meters for the UK site and the Dutch site, or one of the UK sites and one of the Dutch sites. And you can see that the slope and the general sort of topographic context is really quite different between our different field sites too. The red lines on here are the locations of our water level and wave measurement stations. So clearly where there is a rapid decrease in water depth, we have an effect of that on the waves as well as an effect of bed roughness. But all of this is fed into the models, and then we can tease out the relative effect of these characteristics. In terms of the long-term stability of these surfaces, it's clearly important that we gain an understanding of that, because ultimately if the wetland does not survive processes of sea level rise or changing sediment dynamics, then it won't do us a sea defence service. It won't provide a sea defence or flood protection service. So we have also got an extensive network at our sites looking at annual deposition of sediments, which is the sediment deposited on these square kaolinite markers you can see in the top left-hand photographs. And then we are comparing that to a measure of the surface elevation of the wetlands with respect to a very deep consolidated sediment base. And as you can see in the bottom diagram there, that elevation change clearly varies between our sites here, and is both a function of the deposition on the surface of sediment, but also the degree to which that sediment compacts over time and the decomposition rate of below ground root matter. We can start to look at how that relates to spatially explicit discrimination of wetland margin types too. So we have developed a classification mechanism to look at whether the marshes are cliffed, are ramped, or have shore normal ridge and runnel systems which aid the delivery of that sediment, or the erosion indeed of the marsh edge or the tidal wetland edge, to give us a better understanding of the longer term dynamic of behaviour of those those environments. So last but not least, and most importantly, clearly we need to know water depths and waves over those sites, and we're fortunate that we can use high-tech methods now to get self-triggered wave records which are timed to coincide with the tide coming in, which is obviously always slightly different from the predicted tidal times given meteorological forcing and so on. And you can see in the bottom left-hand graph that we have a lot of data for very different conditions, a huge range of different water depths over our wetlands, and a great range of different wave heights over those wetlands. And all of that data is used to calibrate and validate the hydrodynamic models that then feed into the MI-SAFE package. It's instructive here, although we're validating the models with that data, really it's instructive just to have a quick look at the empirical evidence that this shows us. And you can see here that, clearly in the areas of our transects where there's no vegetation, there is very little change in the wave heights, and this is signified here in these brown boxes. So the wave heights over that section change hardly at all. When you get into the vegetated part of our wave recording transects, you can see a negative change in wave height across those parts between 20 and 80%, depending on the conditions, and also depending on the type of vegetation. So we've got reed beds in the top two plots and marsh vegetation in the bottom two. So this data then feeds in to calibrate the models, and at this point I will hand over for you to find out a little bit more about how those models are built and how that then feeds into the MI-SAFE package.
Thank you, Aris Muller, for this clear explanation on the fieldwork done. Now, moving to the modeling of flood hazard parameters that are relevant for the engineers. I give the floor to Kees Nederhoff of Deltares, who is and Joan Sala Calero, who is as a duo waiting to present in the next 50 minutes on the modeling and the data integration that is the basis of the online MI-SAFE product package. Here you go, Kees.
Thank you very much, Mindert, and thank you very much, Iris and Daphne, for a very thorough introduction in remote sensing and the fieldwork. I'm going to focus a little bit more on the engineering aspects of vegetated foreshores, and specifically related to the wave attenuation. So what I'm going to talk about is first of all the inputs of what you actually need a numerical model. That means bathymetry and intertidal bathymetry and topography. Focus a little bit more on where we can get the waves and water levels, and focus on the vegetation presence and type. After that, I will switch gears a little bit and talk more in detail about the numerical model of how we can actually solve wave attenuations on vegetated foreshores. And then secondly, you can also focus more on the overtopping. And the goal that is set in FAST is kind of ambitious, because we're trying to do this not on one specific location, but we're trying to do this globally on every location in the world. So that means that we need bathymetry data for every location in the world. This graph is an example of the combination between GEPCO and SRTM, which are both fairly known data sets for both deep water bathymetry and topography. However, a problem that engineers often encounter with is that these data sets don't really connect very well. So this so-called intertidal bathymetry is fairly absent, relatively unknown. So that therefore we had derived a second data set, a so-called intertidal bathymetry map, which describes in fairly high detail really this connection between the more deeper parts of the foreshore and actually the topography. I think Daphne already talked a little bit of how this data set is created, so I will not spend too much time on it, but I think it's a nice example of how global data sets like the Sentinel data in Google Earth Engine can be combined with hydrodynamics values of the highest and the lowest astronomical tide. After you've constructed the bathymetry and the topography, you would like to assess what the effect of vegetation is on your foreshore. So therefore you need to know where the vegetation is and what kind of type you can use. This is an example of a worldwide vegetation type map. There are more detailed maps available. For example, in Europe we use a higher quality data set, but in principle you would just like to know what kind of vegetation do you have, and you need a data source for that. And this is a example that we used for the vegetation type globally. And after you derive the vegetation type of the presence and the type, you would like to know a little bit more about the water levels and the waves. And since the 80s there are data sets, meteorological data sets of pressure and wind speeds, which makes it possible to derive storm surge levels around the globe with a certain return period. And the upper panel is a good example of that. It's created with the global tide and surge model developed by Deltares. And the lower panel is a typical example of the ERA interim wave database or reanalysis data set, showing the same plot and showing the significant wave height with a return period of 1 in 100 years. And these kind of data points can be then used for every transect in the world to assess what vegetation can do to mitigate or to reduce the wave attack during extreme conditions. That was so far a little bit more about the inputs that we can use. Now I would like to focus a little bit more on the numerical model we're gonna apply. XSpeech is, well, originally it was a morphodynamic model used to model dune erosion and overwash. However, nowadays we also have implemented the so-called vegetation module, which makes it possible to reproduce the effects of the impact of vegetation on the incident short waves, on the infragravity waves, and on the wave setup. And we have done that by schematizing vegetation as a certain height, a certain diameter, a certain density, and a certain drag coefficient. Of course, that's a big simplification if you compare to the field work that Iris, for example, did. But in a numerical model sense, you need to schematize in order to simulate it a little bit. However, we do allow for vertical distribution of vegetation, which is needed if you would like to model mangroves, and also for horizontal distribution. And how that then looks like is something like this. You have the upper panel that shows the incident wave heights in the so-called non-hydrostatic model where you don't see any vegetation. And in the lower panel you see the same wave basically coming in, but then there's some vegetation presence. And as you can see already quite clearly visually, the vegetation has a quite significant effect on the wave heights, and this we can talk about wave attenuation. How are we actually solving this? It's the following. So like I said, the non-hydrostatic mode results really the incident wave shape, and we take vegetation into account by including a so-called drag force in the momentum equations. For the people that are fond on equations, the momentum equations as you know them in 1D, and basically this F that you can see here is an extra force that you can put in the momentum equations, which is related to the vegetation and which can be integrated over the height. And since XSpeech is a depth average model, we always need to integrate over the entire depth. This is one implementation in the so-called non-hydrostatic mode. You can also use a slightly computational, more efficient mode, which is the so-called surf beat mode. Again, you see the situation without vegetation in the upper panel and the situation with vegetation in the lower panel. The difference here is that we have the so-called infragravity waves within the light blue colors, which are the long waves, and in the darker blue colors you see the short waves. And the difference are that if you're standing at the beach, you will see the short waves, and the long waves are actually which is dominant in the swash motion. The implementation then requires the difference. So vegetation has both an effect on the short waves and on the infragravity waves. For the short waves, we use a fairly simplistic dissipation formula, which is proportional to the wave height and to the sediment properties and the wave number. And for the infragravity waves, we use again this momentum equation that you saw again, and then you both an effect on vegetation on the infragravity waves in the mean flow, and using an effect on for the nonlinearity of the waves. This is more like a summary because this can maybe be slightly fast for people. If you would like to read more about it, there are 2 papers out there, both from my colleague Van Rooyen, both in 2015 and in 2016, which summarizes these equations and how it's implemented in the numerical code. Then the step towards what we actually did in MySafe. What we did is we have pre-computed X-speech simulations for a number of situations. This is needed because we would like to, on the fly, give you an answer on any transect in the world. So it's not possible to calculate do the simulation while you click on the browser. We need to have a pre-computed X-speech simulation ready. And what we then do for a range of conditions of wave heights, steepnesses, water levels, vegetation types, and coastal slopes, we find out for a transect in which category this transect falls, and then present the results of this pre-computed X-speech simulation. And how that then will look, you can either base these results on global data. That means you use data available at every place on the world. This is the so-called educational version. Mindert will talk more about that a little bit later. But then you can see what the wave height is and what the effect is of the vegetation on there. And it's also possible to do a little bit more sophisticated method in that sense. If you have local data, you would like to use that local data specifically, or you have your bathymetry, or you have the vegetation presence, you can calculate it in much more detail. That is the so-called expert version, and this is what you see an example of right now. I think with that, you have an overview of the input data and of the model that were actually used. And now my colleague is going to talk a little bit more about the system architecture and more about the back end of the process.
Thank you, Kees. Johan, you can. I will give you the floor. The audience, you can still ask questions using the questions panel. We will try to answer them in the questions session that is coming up after the presentation of Johan. Johan, I give you the floor now.
Thank you, Mindert. Thank you, Kees. I'm going to be presenting a little bit the work we've done on Work-Packet 5. I'm going to talk about how we use the data in the platform, what does the system architecture look like, and what components are there. And let's go. Oh yeah, here we go. The MySafe viewer is the visible part of the platform. Well, you can see a map on the right side, and on the left side we can see the results tab, the data tab, and the wiki tab. On the data tab is very interesting because we can select all the layers available and preview them directly on the map. We have a legend also. For every layer it changes. On top of that, we can go to the study sites. We can move from one to another. It's in the middle position. And we have 2 navigation controls, the zoom and the location bar. On the down of the screen, there you can see the issues form, where you can contact us with any question you have, and the community links. Following slides presents the system architecture. It's a very complex software tool divided into many components. The visible one is the MySafe portal. That portal handles the user interaction with the clicks and the map, and it's a web-based application. Sends the processing to the backend. The backend is a WPS service based on the OGC protocol. And we have also in the logic and the model tier, we have the X-speech running the model. Behind that, there is the data layers that are stored in a GeoServer. It's an open source component that implements the OGC protocols needed for the website. That is the WCS, Web Catalogs service. Sorry, the WMS that handles the map previews to the web portal, and the CSW that we use for the cataloging. We have also an instance of GeoNetwork to describe all the layers we have in the platform. The transect results, the pre-calculated transect results, are stored in a PostgreSQL database and with a PostGIS extension. And behind all that, we have a file system that holds all the layers. And well, to mention here, we have all the generated layers with the Google Earth engine from Earth observation data. Here we go. If we take a look at the workflow or the algorithm, when a user clicks on the interface, the first step is to obtain a 2-kilometer transect perpendicular to the coastline. We have an OpenStreetMap coastlines dataset that is an open source dataset. Once we have that, we are going to extract all the data for this specific transect. We first need to look at the search and waves levels from the DIVA dataset. We do that for a return period of 10 years. The next step is to merge all the elevation, bathymetry, topography, and intertidal of the transect. That is done by the WPS process. On the fourth step, we look at the vegetation data. The vegetation presence is a data set which has 0 or 1s, indicating the presence of vegetation along the transect, and the vegetation type. So for each cell, we gather what type of vegetation is there. Finally, we put all this together with the sort of the questions that Case presented, and we calculate the attenuation and the required crest height. On the layers panel, you can find these layers for the coastlines and the DIVA. You can find them on the global sub-menu. Then the elevation data, as I said, the GEPCO is used, bathymetry, SRTM on the topography, and in the middle we have a precise intertidal elevation. We merge those data sets, giving priority to the intertidal elevation. And finally, the vegetation data. This can be seen along the transect by a green line, as you can see in the first figure, and the vegetation type that we extract directly from the CORIN dataset for Europe, and the globe cover for the rest of the world. Now we're going to move to questions, if there are any. I'm going to...
Thank you, Johan. Let's move to the questions. I think there are a number of questions already posed, but I cannot read them. We thought we are going to handle some typed questions first, and then go to a round of questions from the audience in audio modus. We have a question on the diagram with wave height, steepness, water depth, and the effect by any growth on the foreshore of Chris van Son. I guess it's a Dutch name, but you never know. I will post that. I will put that question to Case. In case you can switch on your webcam and answer that question. I'll talk about that question. Yeah.
Sure. If I understand. Oh, I'm muted? Yeah. Okay. Okay. If I understand the question correctly, Chris, you're wondering if we are simulating any wave growth on the foreshore itself, and the simple answer is actually no. What we're doing, we're using a return period of 1 in 10 years, or you can basically do whatever, but in the web interface we 1 in every 10 years, and we have a matching significant wave height and matching storm surge level. And that storm surge level is imposed at deep water conditions, so say minus 20 meters, and then propagate it towards the shore. So there's after that no growth of the wave anymore happening, which is indeed an uncertainty or a thing that can be improved. However, based on our experiences, we see that the wave growth on, well, those relatively minor cross-shore distances are fairly limited. I'm not sure if this answers your question, but can anyone give answer? So that's the first question that we had. I think we can say that's answered, or?
I think you can go on, I think, with the next question.
Oh.
Hello, can you hear me?
It is Chris?
This is Chris, yeah.
Oh, Chris, we can hear you.
Yeah. You are far away.
I had my microphone muted, but now you can hear me very clearly now, I hope.
Yeah,
and,
yeah, I can hear you very clear. Yes, I can.
Kees can hear you too. Kees,
all right.
You can also
okay.
switch on your webcam, Kees. Then he can see. Chris can see you. I will switch. I will mute again. Chris, you can talk to Kees.
I see Kees now. I don't know if he sees me, but I can see Kees. Hi, Kees.
Hi, Chris. I cannot see you, but that's okay.
I don't know how to switch on my. How do I do this now? Anyway, Kees, I was curious. I mean, you're talking about wave height, wavelength, and everything, and water depth. And the water depth has influences on the wave height. The wind has influences on the wave height. You are reducing wave height and length by having some growth on the foreshore. What's the, well, then I'm not going to details. For instance, where the water is no more than 10 meters, there's a lot of, organic, or how do I say, tornado forces of wind. And then what is happening? I mean, these waves are being pushed forward by the wind.
Yeah, so the general idea is that we have these two data sets, both the global tide and search model and the area interim data sets, where larger scale meteorological patterns are resolved and their impacts on wave heights and their impacts on storm surge levels. And we then impose them relatively close towards the shore and then propagate them towards the shore itself and looking at what the attenuation of the vegetation is. You're talking more in detail about what exactly happens to that specific wave on the foreshore, matching the certain wind conditions, and there is indeed a effect. But if you look at the larger scale patterns and looking at a proxy of the wave height, you in general see that the deep water conditions are mainly driven by the meteorological effects that you're seeing, and what's happening in the foreshore, that's much more driven by like swatch processes and wave breaking and that kind of things. And those are things are taking into account.
All right. Okay. Well, if you are talking about big areas, then it's not so easy, I think, to control or to make control of the wave heights and the length.
Yeah, like there's definitely a limitation in there. That's completely right. But in general, like what you do is you simulate 2 kilometers cross shore. That's like sort of the distance that you're using these X-Beach models for. Wow. So you don't model large scale patterns because those are resolved in these larger scale wave and storm surge level models. Mm-hmm. So there's not a dynamic coupling in that, and that's something that you can definitely take into account. If you have the time and you would like to spend more time to really simulate it accurately, you can. But we were trying to give an answer basically everywhere in the world, and you can improve that answer if you have more time.
Yeah, of course, I understand that. Okay. Well, thank you very much for this answer for now. Thank you.
You're welcome.
Thank you.
This is Minute again. Kees is still listening. Shall we go to the next few questions that we have? I see Uwe Dordenbusch with a question. Uwe, I think that's also one for Kees. Kees, can you start? Uwe, your phone is open. We can hear you. Uwe? Okay, Kees, you can you shortly answer that question?
The question is, I'm not sure if everybody can see it, the question is if the 10-year return period. 2 questions, why not 200? And the 1 in 100 return period, can that be combination with water level and wave? Which did you use? I think it's just an arbitrary chosen 1 in 10 years. In principle, there's no reason why to use a 1 in 10 instead of a 1 in 100. Of course, if you're talking about return periods, you should have a matching return period. Otherwise, you're taking things not completely accurately. So I would not recommend to use a 1 in 10 wave height in combination with a 1 in 100 year storm surge level. But that's more related to what does the return period then even mean.
The data set of Pluim et al. Is containing 10, 100 and 1000 years of the storm surge levels. So we do not have the 200 years available in our data sets. Yeah. Okay, we move to the next question. The next question is from Adriana Camino on the floodplain and river bathymetry issue. Why is it not included in the MI Safe? Shall I answer that? We have been focusing, Adriana, we have been focusing on the coast, and we are confident that if we have bathymetry of floodplains and information of vegetation there, we can apply the system to that areas. But to limit our to keep within our original scope, we were focusing primarily on coastal areas. We have not.
Thank you.
Yeah? Okay, Adriana.
Yes, I'm hearing you. Thank you.
Okay, did you hear my answer?
Yes, I did. Yeah, my question would be more in the, since this is an open source, I was thinking maybe if we can make use of the package that you are presenting and maybe adapt it to our own purposes. For our case would be the floodplains and the river surveying.
Done easily, but we are looking for in our open source and open data community for teaming up with other groups to make that step to other systems that we do not cover yet.
Oh, I understand. Sure, I know which stage are you now. Thank you so much.
Okay, Adriana, thank you very much. Is there another question? Okay, Joanna Grossa, who raised her hand. And then we go to Julia Monroy. Julio. Can you find Joanna? Okay, Joanna, you can speak. Your microphone is open.
Hello?
Yes, we can hear you.
You can hear me. Sorry, I'm Ioana Groza from Romania. Sorry, one question is, I'm not a specialist in modeling, but from looking to this, I wonder if your model, for example, could be applied for a normal river. Yes, you know, we have the Danube, you had the pilot in Danube Delta, but for example, if your model could be used to model the influence of these wetlands, for example, along the Danube, how they could influence the impact of, let's say, high flow that comes sometimes, like was the, I don't know, in 2006, 2008, 2011, and so on.
Yeah, I can answer this very shortly. In principle, if we have the hydrodynamic data on the waves, if we have the information on the bathymetry, if we have the information on the vegetation, which we can get from Earth observation and of course from local datasets, then we can do the same application to any site. And we call this an advanced modality, an advanced version of the package that we have now. And I will explain that later together with Kees after the break. No, after this question session. Sorry, this is not a break, but consider this an energizer for the next round.
And the next question is, okay, do you have this model? How do you transfer this into the practice, for example, of a local authority? How she knows, I don't know, an authority knows that can go to you and know what to do there, or how you put this into the practice? Because this is my question. Now you have this model, it's very specialized with data. Probably if you show that the last slide where you see the waves, he understands something, but not for the rest. How can somebody not specialist understand what is the use in it for it.
Yeah, Jana, this is this model XBeats, what you are referring to, is what we call an open source model with a very large user community of about 10,000 people, and we continuously train these people in using that model themselves and setting up their own schematizations with it. In this spring we organized the Delft Software Days. In this next autumn, in October, November, we organize another Delft Software Days, which we offer opportunities for people interested in this applications of this model with its data sets to get acquainted to it and to make the next step. So this is a thing that has been done before, train users in the use of this software. So we expect that it will be possible with your own group of people that could be interested in using it. I will come back on this in the next round of presentations in a moment.
Okay.
I hope this is clear, and we go now to the last question, which is from Julio Monroy, and then of course all the other questions will be registered by us, and we will be able to come back to those questions through email later after this session. Okay, Julio, are you online? Can I hear you? I hear something, Julio, but I do not know if it's you. Okay, the microphone is off. No, it's on. The microphone is on. I hear something. Oh, he has no microphone. Okay, Julio, the answer to this question is that I will show you what is online after this round of questions. This is a nice bridge. Thank you for this question, Julio, to the next part of this presentation. A lot of this package is online. What we call the educational and the expert products and services, and we will go into that in a minute. And from there you can see, can judge what you can need of those products. Thank you very much. I think we move on now to the next round of presentations. We are reasonably on schedule. We will try to keep the schedule as much as possible. I think I have the honor of starting with the next presentation. I have to change my glasses, audience. I will put off my webcam and, oh, sorry. Okay, here we go. Nothing is happening. Heb ik wel controle? Ik heb helemaal geen controle. Sorry, I don't have control. Sharing. Ik zie mezelf niet eens. Okay. Here we are again. I had some small technical issues. Everything is working. I will talk you through the demonstration of the products that we have online, and then start with explaining on advanced services that we can produce in the MI Safe package together with Kees, and Gloria Peralta of the University of Cadiz will round this presentation off with an explanation on what we can do for you now and after the FAST project in working further together on increasing functionalities and use of this package. We called it the value of MISafe. You have been listening to the presenters of the science part, the last 45 minutes, the science behind MISafe, and on the value we are much more focusing on the use of these products for applications. So what are we looking at? You got some images already in the first 45 minutes on this MISafe package. It's an online platform, and in this platform we are serving out all this data, global data layers, high detail local data layers, and our modeling application. And we produce information there on flood hazard reduction of vegetated coasts for any coast on the planet, quantified in wave reduction on the toe of a dike or on the end of a foreshore, and recalculated into a crest, eventual or imaginary crest height of a dike behind that foreshore. Furthermore, the MISafe package is a team. The team of these 5 partners combined with their expertises combined and their tools combined to be able to deliver the services to you. And it's a community. The community, the open source community and open data community that is being managed and hosted by Deltares, which we are proud of to see that this community is growing and alive and helps us to broadcast these software packages into the world. And the package we are talking about now, MISafe, has in our opinion some unique features. It helps meeting the requirements of professionals that implement nature-based flood defense strategies, and it does that by having online and easy-to-use web application. It is as far as we know, and we have been looking around, the first service offering a worldwide estimate of parameters related to flood risk by coupling these Earth observation data from Landsat and from Sentinel, and the sea level data and wave data and vegetation parameters. It combines a global data set, and it combines local analysis of high spatial resolutions for the study sites in the online modus. It is based on transparent and verifiable scientific insights. We have documentation online, and in the science of documents, which are also online, you can read how we have been doing all the work and how we have been, and you can see there the documentation of our methods and protocols. And it uses these open and standard OGC formats and open source modeling that also delivers access to our online databases. The open source model XBeats, I already explained, has a large community that is working on this model, and that is co-developing the model together with Deltares. And the team, that's us. The presenters of today you have heard, that is helping you to deliver investigations for your site or your challenge, if that is relevant. And the community is there to actively interact with us to further the development of the products and the services. We are linked to these open data and open source communities. Here you see on this screen an example of the XBeats open source community. All this information is available from the Deltares website. We have something called the Open Earth community. You see the red dot, the green square, and the blue triangle, which is a community. It gives you the basic concepts and ideas on which, for instance, XBeats and is developed, and on which FAST is developed. We are very actively building on that community. Here you see one of our directors, the science director of Deltares, Jaap Kwaadijk, focusing on that again. We like to share this data and these models because we think this is the way forward as Deltares to make really progress and on understanding how in our case, coastal systems work and how they can contribute to flood hazard reduction. The FAST project and therefore MI-Safe package is part of the Delft Software Days. We have been spending time in the Delft Software Days the last 3 years already on explaining this software to users, and in 2017 we will do that again. You can go to the Delft Software Days website and find information on what we are planning to do. And on the 31st of October there will be a FAST day with explanation and also hands-on training of FAST applications of using the MI-Safe package. In MI-Safe Online, which I will go to in a minute online to show you something, we have two levels. We have the educational level, which delivers a global coverage. It gives you access and visualization of all the global coverage maps that we have been producing. So that is about elevation and bathymetry, but we have delivered an intertidal area map which has not been existing before. The FAST team, that is a vegetation type and vegetation cover database online, and we have delivered this vegetation cover based on Sentinel data of 2015-2016. There is a waves and storm surge database online, which we use to predict the wave heights and as input for our models. For the educational version, we predict the effectivity of vegetation for the 10% likelihood storm. That's a 1 in 10 year storm. You can go to the science behind all this information online, and you can find videos of all the methods that we used online. And there is also a link here to those videos who are also available on YouTube. The expert level is the high resolution version of the MI-Safe package, where you can go to a study site, of course, and find high resolution information. High resolution information, again, elevation and bathymetry, but now using local dams. Vegetation type and cover, but now using NDVI, high resolution NDVI and leaf area indexes. Using waves and storm surges of 3 different occurrences: the 10%, the 1%, and the 0.1% likelihoods. And we have calibrated the XBeats model on these study sites on the basis of the field data that were collected to make the model really predict in a trustworthy way the expected reduction of waves over the foreshores with vegetation. All in all, this expert level gives you a much higher resolution and much higher quality of predictions compared to the global educational level modality. The viewer is consisting of different subparts. I will go through it very fast. The number 1 depicts, of course, the map layer. The number 2, the mapping layer. The number 2 depicts all the data folders, the map folders that you can switch on and switch off again. Number 3 gives you the overview of the study sites that we have been focusing on for the high resolution expert modality. Number 4 gives you a search bar where you can select any site on the world which has a coast to go to move to and zoom into and do some calculations there. Number 5 is the zoom in and zoom out bottom of the map. 6 gives you access to the database with the online maps. All the maps in box number 2 are available online in NetCDF format and using an INSPIRE convention definitions, and you can download parts of the maps there. Number 7 is the legend of the active map that is shown on screen. Number 8 gives you access to the tweet and the Twitter and the Facebook of accounts of our MISafe viewer, which helps you to post questions and follow the news. And number 9 gives you email access for joining the community and for the reporting issues. Number 10, on the left hand side top, you can see 3 tabs called results, data and the wiki. The data is now active, that shows the folders. The results will be shown in the next slide here, where you can see the results in more detail now. A case of Tillingham is shown here. Number 15, I'm looking on the map screen. Number 15 is showing you the transect of the 2 kilometer transect that we use to make calculations on wave reduction over the foreshore. Number 11 underneath shows you the results, that is the collection of all the data that we have available for this study site. You can see results for the 1% likelihood storm. You can see how the what the water level is, which is the blue box. You can see the green, the brown area, which shows you the bathymetry. On top of that, you see a green line, which shows you the vegetation. And you see 2 lines, blue dots, which is the wave reduction, wave height and wave reduction without vegetation, and the continuous blue line is the wave reduction curve with vegetation. On 12 left top, you can see 3 more boxes called the science behind. Here you find a wiki page describing all the science behind our work, the value of, which I'm talking about now, and the use of MISafe, which gives you videos on how to use this interface. Number 13 shows you that there is vegetation present and that this vegetation contributes, in this case, to wave attenuation. And number 14 gives you all the coordinates of this project, being a EU-funded project in the FP7 program related to Copernicus and with our 5 partners. So let's have a look at the interface itself. I have already opened the fastopenearth.eu. You can go there also if you want. I'm going there now. At least I'm going to try to do that. That is, of course, a piece of cake. Here it is. This is here you can see the pop-up screen of the MISafe tool. In principle, I would like to fill in my email address here to keep track of the people who are using this tool. This screen shows you some information on the background of this MISafe interface, and it highlights that you can fill in a join community form to help us grow the online open source community further. If I agree with our limitations on using this software, I can continue. I cannot continue if I don't agree with these terms. You can also click Contact FastTeam, which will give you an email form to ask questions or propose suggestions, and you can join the community here. I'm going to continue, and that means that I'm now in the online live MISafe viewer. Let's go to, for instance, the data tab, and let's go to Tillingham study site, and I'm now moving blindingly fast to this site. I have been zooming out to give you a little bit of the idea what the fast global imagery is about. I will activate the intertidal area, intertidal elevation map, which we have for all coasts of the world. And I will also add the vegetation presence, which we have for all coasts of the world. And I can also add the vegetation change, which we have for all coasts of the world. And if I put this on top of that, you can see me moving something, and zooming in a little bit, you can see little red spots where vegetation has been lost in the last 20 years. If I do now a calculation outside of a study site is here where you see the blue stripe, that's Tillingham. If I do it here, I just click on the map. It's loading. It's now collecting all the data from the databases. It shows you a 10% likelihood storm event. It shows you the intertidal elevation elevation map, which is this part of the map. The dark part here is the GEPCO depth map, and it shows you a storm surge level of 1 in 10 years. It shows you the wave elevation at the toe of the dike without vegetation and the blue one with vegetation. Furthermore, it shows you a confidence map with all the with information on how confident the databases are that we are using in this educational version for this area, because it changes where you are on the world. It shows you a story telling what the graph is showing you. For instance, you can see that that the intertidal vegetation has a length of 590 meters, that the water level setup is 3.7 meters, that the significant wave height is 3.2 meters for this 10% likelihood storm event, and that the estimated slope of the transect is about 1 in 366 meters. And for the sensitivity tab, you will see that outside fast study sites we are not giving you more information than this, because the quality of the information is limited, and we will not, we do not want to be too confident about our results in non-study sites. So if I go underneath here, for instance, you can see the vegetation map being activated here with a hyperlink, and if you follow this hyperlink you go to the website where you can find these databases described in much more detail, and you can download parts of these databases. Let me zoom out a little bit again, and I go back now. This is the last part of my presentation. We'll go back to the study site Tillingham. I will go to the data tab again, switch this off. Now it's the dull picture, and if we are lucky, I have to make my screen a little bit smaller. I'm sorry about that. I will now blow it up, and I do that by Ctrl+ and Ctrl-. That's a trick to show everything on the screen. You can see what kind of data we have available for a specific study site. So here you see the information of the digital terrain model. It will come up in a moment. It's now being downloaded. Here it is, and you can see the leaf area index and the NDVI information coming from the Sentinel data sets. So you can imagine for these study sites we have much more detailed information available than for the global the coast of the world. I'm now giving you showing you a model result of Tillingham, and beneath that you can see of course now the NDVI map and the dam. I could have been switching on the vegetation, but I didn't do that. But here you can see now the highly detailed results of the calculation. This is a real X-Beach calculation. This is not plucked from a predefined data set. This is calibrated against field data, and you can see now the effect of the vegetation, which is the green sort of line on top of the salt marsh bathymetry. This is the dike behind the Tillingham salt marsh. You can see the wave reduction without vegetation and the wave reduction with vegetation, which is depending on the type of the vegetation. In this case, Spartina salt marsh. If we would have been on a mangrove coast, this line would have been steeper. depending of course on the amount of mangrove vegetation in front of a dike. In the confidence we will see a lot more green colors, but where we have, because we have much higher quality information available, you will see again the context showing you the story of the behind the calculation of the 1% likelihood storm, and in the sensitivity now you will see for 3 likelihoods, 1 in 100 years, 1 in 10 years, 1 in 1,000 years, the impact of the vegetation density on the on a required sea defense crest height, and underneath you can see the storm surge data, wave data that we use to derive this information. Everything that you can see here is explained in the science behind wiki, where a lot of detail can be found. At this moment I'm going to conclude the presentation of the MISAFE Web Viewer, and I will go back to the PowerPoint presentation where we were a moment ago, and that was here. So we have been I have been showing around very quickly, and we move forward now to the advanced level of services beyond what is online available. I will talk you through the first 5 sheets, and then Kees will take over for the modeling part. In the advanced service, we aim for producing tailor-made solutions for users in a interactive fashion. What you can see here is a number of examples of that kind of tailor-made solutions, which Kees will explain in a moment. What we state that the tool, the products and the services that we can deliver allow us to implement advanced services for any location that is possible. For that we need of course the bathymetry and the elevation that we can get from the Earth observation or from a dam. We need vegetation information which we can get from Earth observation. We need information on the hydrodynamic forcing, which we can get from local data sources or our regional models. We need ground truthing to improve the quality of the outputs, and we need to do more detailed modeling to move from a sort of a rapid assessment of what could be the effect of vegetated foreshores to storm surge, to flood hazard reduction, to more a design and evaluation type of interaction with users. And you as a user can add more functionalities by linking to other tools. Everything is open source, what I have been showing you, and that means that we are available to share our knowledge to you by training you to help you make a next step, or even we can make that next step for you if that is required. And for an example, this is an advanced analysis in time. You have of the NDVI and intertidal elevation for a certain area. This means that we have now been extracting bins of data instead of adding them up to one picture, which has been is made available online in the educational version. Here you can see the temporal resolution, which is very important for understanding the coastal processes. That can be done in an advanced modality. We can classify masses to you for any site now, giving that intertidal elevation and the NDVI information on the vegetation densities and vegetation types that are there. We can go to even more high resolution classification of masses if we use the drone imagery. You have seen an example from IRIS, and we have integrated in the Tillingham site, we have integrated the drone image on top of the other images in the online MISAFE package, where you can see how that fits on top of the Earth observation and the dams that were also available. And of the need for field investigations is obvious to link biophysical characteristics of in situ to the Earth observation. We need to do these field investigations to improve the quality of the assessments. We have been discussing with you in the first hour the science behind here. You see some examples of all the science that has been done. Part of this science, part of this work needs to be done for a specific site to get quality information and to do the model calibrations to give you good quality assessments of flood hazard reductions of foreshores. And now I'm moving to Kees to show you what can be done if you apply advanced modeling instead of these pre-calculated sets of data or a data on a 2-kilometer transect, as was shown for the study sites a moment ago. Kees, I'm going to hand over the keyboard to you. There you go. And I'm going to close my...
I have some problems getting... I don't have the control of the slides, but...
Oh, I will try it again, please. Moment. How can I... Now you have the control. Yeah, must be. No? Okay, Kees, if I click...
You can just click for me, Minder. I think that Minder gave a good overview of the transition that you have. At the one hand, MySafe Education, where you in your browser can look at every transect in the world to rapidly assess what the vegetation can do for wave attenuation. And more advanced, if you can use a combination of Earth observation and field work, you can in detail assess a specific case. And in general, an engineering question would be, what is eventually the effect on the inundation? Like you live here behind your little levee, what is the probability of flooding, and can I actually maybe implement some vegetation to reduce the amount of inundations you're going to have? This is a specific case study on Tillingham in the United Kingdom, where one of the case study sites of FAST. The reason that we use this one is that we have this combination of both field data and detailed Earth observation data, and this combination is really important to get high quality assessments or high quality model results, because you can actually validate what you're trying to simulate. To give a quick introduction, Minard already saw it. It's a really extensive marsh, which you can see over here, and you have a little levee over here. And well, behind here, there's not a really big economic area, so maybe in economic sense, it's not the most pressing issue. But I think it's interesting to look at the effect of the vegetation of the salt marsh on the wave attenuation and eventually overtopping and the inundation. I think this shows the combination of basically the science behind MySafe, of the science in FAST, explained by Daphne and by Iris. It's a combination between fieldwork at the one hand in combination with Earth observation data at the other hand. Because of course it's really time consumptions to really assess what kind of vegetation you have. You can do that of course at every single plant. However, if you combine the left image with satellite data, you are able to, of the entire marsh, of the entire area, assess what the vegetation is. And then this color difference is, by the way, the leaf area index. So the greener it is, the more vegetation you have, and you see a clear difference between the summer bed and the winter bed at the right side. In this animation, you see a typical XPIC simulation. In this case, we don't limit ourselves to a transect, but we're actually simulating in 2D. You see the waves propagating from deeper water, and then eventually hitting the marsh, which you see in the green. And this higher area over here is the levee. And the simulation maybe takes slightly too long. If I extend it, you see eventually the entire salt marsh is submerged and a substantial amount of inundation or overtopping occurs. what of course is interesting, if you run this simulation with and without vegetation in trying to quantify what the effect of the vegetation is on the overtopping and therefore the inundation. And that's actually the second part you're going to see. Again, you see Tillingham, but at the left side you see the situation without vegetation, and at the right side you see the situation with vegetation. And you start to see like some water starts overtopping, but no real severe inundation occurs, but later in a simulation it does. You see these color differences represent what the water depth is behind the levee. And you see quite clearly that the color intensities at the right side in the situation without this vegetation are much more intense, meaning there's much more water overtop the levee and much more inundation is occurring. So these advanced tools makes it possible for you to quantify what the effect of vegetation is, and then you can start asking questions. Would you like to raise your levee height, or would you maybe implement some vegetation that can reduce the amount of overtopping and therefore the amount of inundation that can occur? Some conclusions of the advanced part of MySafe is the first one is related to the intertidal regions, which is in engineering terms often a problematic area because you don't have that much data there. And I think that FAST made a really beautiful data set publicly available for these intertidal areas, which is available on the web if you look for it. Secondly, the time series of the big data is really promising and now feasible using these Google Earth Engine and other facilities to actually use the satellite data. And related to the satellite data, Sentinel is therefore really a useful one for more specific and high quality data, but the downside is that it's not up for so long in that sense, so therefore you're sticked to older data sets if you would like to do some more data analysis for a long-term time series. And then within FAST, we derived specific algorithms to link what you actually see in the field with what you can actually observe, or what you actually can observe from a satellite, and then combine that in a numerical model to have a flood hazard assessment. And I think that the large applicability is to focus on more local situations that you can first assess with your MySafe educational version, and then actually make a local situation and focus on what the potentials are of vegetation over there. And so far, I think we've seen a lot of synergies between the different types of fields. So on one hand, you're more the remote sensing branches versus more the engineering modelers. And you see nicely that these things can come together and actually provide something useful for society in talking about reducing flood risk for people that are vulnerable for that. And I think that this is actually just one of the first steps in that sense, that we can do much more. And I think it's really important to emphasize that the involvement of the entire community is really important in that, and we can make the next step in that. I think that this is the part of Gloria.
Thank you, Kees. Thank you, Kees, for this explanation. I heard from the audience. I was reading that the website is not online on the external server. We encounter at this moment something we call the firewall problem. I'm not an IT specialist. We are working on that. It's unclear for me what is exactly happening, but we will get it online ASAP. Gloria, I'm going to give the screen to you to give us the last part of the presentation, and then we can go to the question round. Okay, Gloria.
Thank
Here you go.
very much. Yeah, I think I have it now. Okay, so I'm gonna be the last speaker of today before the last questions. Sorry, before the second round of questions, and I'm gonna speak a little bit about what is gonna happen with MySafe services after the FAST project, because after a few interviews we have, well, after many interviews we have with our end users, all of them ask if this is related to a European project, what is going to happen when the project finishes. Well, the thing is that the viewer, that is the main access to all the services of the MySafe package, is already hosted in Deltares webpage. So this is the viewer is going to be all time available through Deltares software webpage. And not only the viewer, but all, sorry. but also our services are gonna be available. In particular, the educational and the expert level services that Minder showed how to access through the viewer will continue, of course, being free and accessible via the MISAFE viewer. These levels of services are granted after acceptance of our non-commercial service level agreement. Right now, when you access to the viewer, you have to accept the disclaimer to access, but very soon we will add the list of conditions that you need to accept to use the viewer. One thing we are aware is that the educational and the expert level services may get dated with time after the FAST project finish. However, we expect that with future projects and with the input of the advanced level services, we are going to be able to update some or most of these services. About the advanced level services, well, the FAST consortium that is together for this project will remain active after the life of the project to provide the advanced levels of services. The provision of these services is going to be granted after the acceptance of the corresponding commercial service level agreement. And this commercial service level agreement is going to be personalized case by case after interaction with the FAST consortium. So if an end user has a specific request, they only have to contact the FAST consortium, and after having an interaction, then we will specify what needs to reach the request, and then we will personalize that service level agreement. How to contact with the FAST consortium? Well, during the project and for a few years after the project finish, it's very easy to contact with any member of the FAST consortium by going to our webpage and seeing the details of the team. Nevertheless, after independently of this, you can also contact the FAST consortium by using the MISAFE viewer. When you access at the beginning to the viewer, you have a couple of ways to contact us. One is by clicking in the contact the FAST team, and that opens an email address to send your request. And you can also contact us by filling in the form of the joint community. Other ways to contact us is via the social media. We have a Facebook for the FAST project and 2 Twitter accounts, one for the FAST project and another one specific for the MISAFE services. Finally, we would like to invite you to join the community in case, well, of course, for all the convenience that Minder already described, but also in case you want to be updated with other interesting webinars and any update on the MISAFE service. To join our community, you only have to click in the button on the pop-up screen and fill in your data, and then we will send you the information every time we have it. I think this is the end, and then Minder, if you want to.
Thank you, Gloria. I thought this was quite a complete presentation in this way. We still have 15, no, let's say 10 minutes for questions, and let's move to some of the questions that were asked online already. Katerina is there. Katerina, are you there?
Yes.
Okay, Katerina, I can read your question online. I think that question is something for me. I can start answering it, Katerina, and then I will ask the other scientists to join us in the discussion. The question is, what is the reliability of MISAFE in areas outside of the study areas, for example in the Mediterranean? In a sense, the data sets outside of our study sites are not calibrated and are on a more on a less detailed resolution. If you go to the confidence tab in the calculation results part, you will see that you have less quality data. That means that using the MISAFE viewer for in its educational modality for a coast in the Mediterranean will deliver less quality results, and moving to a higher quality results will mean that you need to interact with the team to put in higher quality maps to make the next to move to a higher quality of output.
Okay, but still for this site you have, let's say, data from satellites, for example.
Yes, we have, and we have data of satellites, but for instance, the Mediterranean does not have a very big tide. It has practically no tide. That means that our intertidal map is not very helpful in deciding on the bathymetry and the elevation. And we have, of course, a vegetation cover map and the salt and a salt mass typology. This will be of reasonable quality, but if the salt mass characteristics deviate from the Spartina masses that we have been using from our calibration on the study sites, the results will be less precise. So it depends a little bit on the area where you apply the model, how good the output will be, and it will be better in areas with more tides, because then the elevation mapping will be better.
Okay, thank you.
Next question. I don't see the name. Okay. Sejong Lee, I can see that. Iris, I think this is a question for you. Sejong, can you hear us? Sejong asks us, it seems that all the pilot schemes are related to temperate wetlands. Is there a similar effort to do the same for tropical wetlands other than mangroves? Iris, can you join the discussion on that? Or Daphne?
Yeah, I can. There is also a question from Katerina before then as well to me, but I'll answer the one from Sejong Lee first.
Okay, you can switch on your webcam, Iris.
Okay, I shall do that. Okay, I hope this works.
It works.
So thank you, Sejong, for asking this question. It's, we had to be limited to our temperate wetlands for the project here, particularly. We are, I think, across our groups working in various other projects in tropical wetlands. But there is a lot more to be done in tropical wetlands, including mangroves. So I think, you know, one of the things to say is that with our studies here on the temperate wetlands, it will be very interesting to see how transferable some of the relationships are between the characteristics of the wetland vegetation and the effect that has on water movement across those surfaces. And we can clearly, you know, start to do that by looking at some of the existing studies that have looked at both storm surge reduction and wave reduction in tropical wetlands, and there are some of those. So there is some information already out there on case studies, but linking this to Earth observation data has not so far been done, and that's clearly something that, you know, we could do into the future, and that would come under some of the more detailed work we could build in terms of, you know, moving forward from the FAST project. Shall I ask the question by Katerina Rippey as well? Mindert, I cannot hear you.
This is a good idea. You go to Catherine now, and then we go to Thomas, and that who asked questions to Kees. Okay.
Okay. Katerina, thank you for that question too. Yes, you are correct. We are using our field measurements of the presence of vegetation, the characteristics of the vegetation, the relative proportion of soil, the characteristics of the soil and water within each of the pixels effectively that relate to the Earth observation products in order to validate what we see from space. And we're using our drone images as an intermediate scale in order to do that. So I hope that answers your question.
Okay, but we understand how it works.
You are very difficult to understand, Katarina. I hear an echo.
Sorry, I cannot hear you very well.
There are connection problems with you, Katarina. We will move to the next question of Thomas. Thomas van Velen, who has a question for Kees, I guess. Kees, can you go answer that question?
Yeah, I can.
Can you repeat it? Can you repeat it also a little bit?
Thomas was asking a question related to the modeling, how the leaf area index is used in XSpeech, since in the numerical equation she saw only the influence of stems and the stem diameter. Well, first of all, Thomas, thanks for the very you're a really good observant in that sense. You're completely right. The trick is that you, based on, since this is a field case, we do know the height of the vegetation, and if you do know the height, then you can estimate the rest of the parameters. However, in the numerical model, since it's depth average, you don't take into account these individual plants. So you calculate, in that sense, an average drag coefficient in the water column. So, valid point. I think this shows the necessity of having some field information. But after that, in the numerical model, it's again combined as a simplistic drag coefficient. I hope that answers your question.
Yes. Okay. Yeah. Thank you very much. I hope there is also some information about it online. I haven't studied all the documents, I have to admit.
On the website of MySafe, on the public wiki, if you can go there, if you're on fast.openearth.eu and you click on the science behind, we have actually a table of all different vegetation types that we've seen in the case studies of FAST, showing also their values that they have. So if you say you are at a different area, which is where you don't know anything about the vegetation properties, you can find some kind of range values, which is observed. So maybe that's useful if you would like to apply that.
Okay, I will check it out. Thank you very much.
You're welcome. Time for the next question.
Okay, we have a question from Nathan Richardson, has left. Okay, then we go to Patricio. Patricio, are you there? Kees is reading the question now. It's on the effect of the vegetation on a hydrostatic and a non-hydrostatic model. Patricio?
We can still answer the question, okay. Of course.
But a moment, Kees. In the meantime, our wizards of the software and hardware department have got MySafe online. There was a problem with the firewall. Okay, Kees, it's yours.
Yeah, Patricio Wickler asked a question about the difference of vegetation in the so-called non-hydrostatic XSpeech model and the SurfBeat model. In principle, we made the model formulations as such that they reproduce both in a similar manner. I do need to say that for the SurfBeat model, we needed to have an additional formulations in the momentum equation in order to make sure that these forces were correct. So if you have the computational power and the time, I would recommend if you would use the non-hydrostatic model. However, the SurfBeat model has performed fairly accurately in the past, and you can also see that if you look at the paper of Van Rooyen 2016, where we compared it to multiple lab experiments showing that we were both capable of simulating the wave attenuation and the wave setup both in the non-hydrostatic and the surf-beat model. However, the surf-beat model was a little bit more challenging, and if you would like to know the details why that was challenging, I would say that look at this paper and you can see a little bit more why that actually was the case. I'm not sure if that answers your question, Patricio. Well, then we assume it did. Mindert, I think I answered that.
I think we reached the last question. This is a question of Thomas, because we are now in the end of our the last seconds of our meeting. Thomas, you had quite an extensive question. I think that's something worth to email you about. But we have put much effort in calibrating the model to the data sets that we have been collecting in the field. A lot of that is in public deliverables from the FAST consortium team. A part of that is not yet available because our PhDs are still working on papers that describe what has been analyzed. I suggest you go to the Science Behind wiki page from our MISAFE interface to start reading there, and if you go to the top level of the wiki, you can find also public documents, public deliverables of the FAST team that could help you further. And please get in touch with us. Also, the other audience, get in touch with us after this meeting by joining the community. Leave your email addresses, and we will be happy to interact with you in the future. And hopefully we will meet somewhere in the conferences that we are active in as a FAST team, and the Delft Software Days International in October and November with a special FAST MISAFE day in which hands-on training is available. So I think we conclude this meeting here. Thank you for attending. It was a great experience also for us to be able to share with you what we have been up to the last 4 years, and there will be another webinar on 22nd of September, and that will be more focused on an earlier time slot to allow also the Asian part of the globe to attend in a nice time of the day. Okay, thank you very much again from our team, and hope to be in touch in the future. Bye-bye.